Hello, everybody. All right. My name is Austin Howard. I'm a PhD student at the University of Texas at Dallas. I work in the Nanotech Institute. Everybody else with the nano shirts on today. I work particularly in physics, and actually my research is in what I think is a particularly cool topic, which is superconductivity. And so I'll be talking about that today. You guys will see, hopefully, everything will work, and you'll be able to see kind of one of the applications, and we can talk about more. Before I get started, I wanted to show a little clip. If you've been around, if maybe any of you have come to some of the earlier talks, or you've been talking to some of the people today, there's probably been a lot of words being thrown around. Nano, you may have heard some numbers, you may have heard 10 to the minus 9 billion, a lot of numbers. I want to show a little video which might give you a little bit better of an idea of what kind of scales we're talking about when we say the nanoscale. Nanoscale is so small that you can really barely imagine. So this comes from a very cool website, and if anybody's interested, I'll give you the link later on. But it starts at the scale that we're used to, the scale of you and me, versus scale. And if we go down, you'll just be able to see really how incredibly small the nanoscale is. As we go, I can skip past the first part, we know some of these things. We know the scale of a basketball, we know the scale of a mouse, of an egg. Now we're getting into things which are a little bit smaller. Maybe it's small for you to hold in your hand. We have marbles. How about a grain of rice? It's a little bit hard to hold a single grain of rice in your hand. Let's go down even further. Now we have, how about the width of a single hair? Can you imagine, can you even see a single hair? No, not really. So we're already at the point where you can't see it with your eyes. But we have a long way to go before we get to our scale. So this is about the smallest you can see just with your eye. Then we have something like a droplet of mist. Maybe you've gone outside when it's a foggy morning, and you see that it's fog everywhere. A single drop of those, you can't even see them. What else do we have? We now have some cells. So cells, the things that make up you and me, the things going in your blood. If you've cut yourself and you're bleeding a little bit, a single cell inside of that. What else do we have? We have, now we have viruses. We don't like viruses, do we? Viruses make us sick. But viruses are so small. Now we get here, this is about where you can see, even if you have a microscope, even the most powerful microscopes, like optical microscopes that you look through in the world, this is this scale. So now we're getting things you can't even see them with the most powerful optical microscope in the world. So we have some more viruses we don't like. And then, after that, you can get to this region. And here is where we have what we talk about when we say the nanoscale. So we have two of the most important types of nanomaterials that people work with are nanotubes and buckyballs. Nanotubes are like little pipes, but the surface of the pipe is formed with only carbon atoms. Anybody by chance know another place you might find a carbon atom? Any ideas? Anybody write with a pencil? Your number 2 pencil in school? You know what's in your number 2 pencil at school? Any guesses? Graphite. And what's graphite made of? It's made of carbon. Graphite is a form of carbon. There's also, the young ones in the audience won't, but maybe the young ones' moms will have a diamond on their ring. Diamond is carbon. It's just in a different arrangement. Just another form of carbon, still pure, 100% carbon, is these carbon nanotubes. Or you can also, instead of having a pipe, you can have a little ball. It looks actually just like a soccer ball. You can also have, and you can have single layers. You can have like a sheet of paper made just of carbon. So there's all sorts of forms of carbon, and all of these are important because they are on this nanometer scale, which is so small you can't see it with your eyes. You can't see it with the most powerful microscopes in the world. The only way you can see it is through special microscopes, which don't even use light at all. So I just wanted to kind of set that little bit of a stage. That's what we talk about when we say nanoscale. Very, very, very small. Now, in particular, what I work with is, like I said, superconductivity. But before we talk about superconductivity, we should talk about the non-super variety, which is just regular conductivity. Does anybody know anything about electricity or how electricity works? All right. You have an idea? Maybe if you go to your house and you have an outlet, you plug something in the wall, and it works on electricity. All right. What's flowing that makes electricity? That's right. That's right. A wire conducts electricity. But when we say it conducts electricity, what's happening? Is it just something magic? Is something moving? Is the wire changing? Okay. 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 But the important thing is what's moving when we have electrical flow. The answer is these little bitty particles called electrons. Anybody heard of electrons? I know you have. Some people back there. Okay. If you have the nano shirt on, I hope you've heard of electrons. Um, Electrons, if you remember the scale I was going at, well, you have to keep going a long way before you find electrons. You actually have to get to the point where you can't see them with any type of microscope at all. Electrons, in fact, are so small that they're used for extremely powerful microscopes. Light itself is too big to see some things, and you actually have to use electrons. So electrons are extremely tiny particles, and they are what move when you plug something on the wall and it works. And the motion of these electrons is what causes a current to flow. Now, I want you to imagine for a minute, imagine you're an electron. So you're tiny, you're trying to move through somewhere, okay? The problem is that you're not just moving around in an empty room. You have to move through this wire. And the wire is sort of like all these chairs in this room. So if I'm an electron, I'm an itty-bitty electron, I need to move through the wire. The problem is I have to climb over the chairs. I might have to push some of you guys out of the way. There's a lot of stuff in my way. And the fact that there's all these things in my way means that it takes some energy for me to get through the room. So in the same way, it takes some energy for these electrons to keep pushing their way through the wire and keep pushing everything out of their way. Okay? So what that means is that you have to keep putting energy into it, and that basically is the reason that things don't run forever. There's this property, and what we call it is resistance, because the wire resists the motion of these electrons. Okay, so that's conductivity. So some materials, like this thing I was saying, some materials allow for electrons to flow easier. So like copper wire is pretty good. Electrons can get through it without much difficulty. They still have a little bit of a difficulty, but they can get through it without much problem. Then there's other materials like, for example, plastic, the insulation around a wire. The plastic is really hard for electrons to move through. So different materials have different resistances. Superconductivity is a special state that some materials can be in. And when they're in this state, the electrons can actually move through the material without any resistance at all. It's like they can pass through the material invisible without even being detected. So superconductivity occurs basically when you measure zero resistance. And the trick that the electrons use, the material itself doesn't really change. There's a trick. The electrons decide, instead of going through one at a time, they pair up. So maybe you and me, so we'd become a pair. So you'd go through and you'd push one chair out of the way, and I'd pass through. Then I'd push the next chair out of the way, and then you'd go through. And so if we work together as a team, we can get through the material without encountering much problem. And that's essentially what happens with superconductivity. Instead of the electrons going through one at a time, they form up in groups of two, in pairs. And these pairs are able to travel through the material without running into any problems, and they can travel through with absolutely no resistance. Okay, so that's what superconductivity is. Now, why is this important? How does this matter? Well, one of the first things that you might think of mattering is what if instead of having copper power lines, what if you had a superconducting power line? So you know, if you drive down the road and you see the power lines overhead or the wires in your house, there's all sorts of energy losses all in those wires because all the electrons have to push their way through. If you replace all of the wires in the United States with superconducting wires, we could save about 30% of our energy usage every year, or 30% of the energy usage at any given time. We basically lose about roughly 20 or 30% of our energy just with electrons trying to push their way through wires and causing heat. So that's one way of making things more efficient, right? You replace everything with superconducting wires. Another application, something that's really cool, is if, let's say, instead of just a straight wire, what if you made a loop of this wire? All right, so something can go around it, doesn't ever have any resistance, never has any problems. What do you think would happen if you made a loop of wire and you started it going and it was a superconductor? Do you think it would ever stop? No, it won't. And that's what's so cool. And actually, there was an experiment when superconductivity was first discovered. This was about 100 years ago. It was first discovered. They still didn't really know what was going on. They didn't know how it worked. And so the guy who discovered it, he made a loop of wire. And he made a superconducting loop. He started a current going in it, and he left it going for years and years and years, and it never went down at all that he could ever measure. So it would be a way of making making new batteries. You could make a battery which had these little loops, and you have the current flowing forever in them. Imagine that you, instead of having that junk drawer of batteries at home that have all gone dead because they've been sitting there too long, they're superconducting batteries. They'd last forever. They can store a lot more power, so you don't have to change them out of your digital camera once every 3 days. So you can have a higher energy storage density, and they can last for a lot longer time. So with batteries, we have conduction, and then we have another very cool application, which is what I have been showing here. If any of you came by earlier, you would have seen it done, but I can show it again once more if it works. Something else that superconductors do, besides having no resistance, is they can spontaneously become magnets themselves. Okay, anybody, show of hands, who's played with magnets before? Anybody play with magnets? Magnets are cool, right? You got the North Poles and the South Poles, and you can't push them together one way, but they stick together so nicely the other way. Right, so magnets are fun to play with, but superconductors are like a special kind of magnet. So normally, if I give you a magnet, maybe it's a magnet on a refrigerator or like a horseshoe magnet, there's a North Pole and a South Pole. You guys remember that? Seen that? So superconductors don't really have a North or a South Pole. What they do is they become magnets depending on what other magnets are around them. So let's say that this is in its superconducting state. It's not right now. It's not cold. I'll get to that in a minute. But let's say it was in its superconducting state, and I set it down on top of a North Pole of one of these magnets here. What will happen is that this superconductor will make itself a North Pole, which is touching whatever North Pole of the regular magnet I'm touching. So you'll have two North Poles facing each other. And if you remember, two North Poles facing each other, they repel. So what ends up happening is if you have a superconductor and you set it on top of a magnet, it'll make its own magnetic field, and it'll repel. They'll push apart from each other, and it'll actually float in the middle of the air. It'll levitate in space. And that's what I'm going to show you right here. I'm going to set the mic down for just a second. All right, so here I have a superconductor. Now this, very, very cold. I'll get to that in just a second. This material, do you see how it can swing back and forth? And if you look closely, and afterwards you guys can come up and look even closer, but it's not touching the magnets. It's floating about, it's floating maybe 1/4 of an inch above the surface of these magnets. And it'll just swing back and forth until it warms up. And now that it's warmed up, it doesn't float anymore. Now it just sits on top. So this floats in midair above the magnets. You can also do the reverse, where you have magnets floating above the superconductors. Either way it works, because it's just like, sorry, forgot. You just have it's like having two magnets, two North Poles facing each other. So this can be used for something. Anybody know about maglev trains, the really fast trains? Maybe you've read something about them. A lot of them use that, yeah. That's right. Maglev trains are a special kind of train. Now we don't have, as far as I know, in the United States, right? But there's several of them over in Europe, and right. And so these maglev trains, they don't roll on tracks like the trains. You've seen train tracks and the trains rolling along, and there's wheels, right? And it's loud, and there's clanking, and it's kind of fun, but it's not very efficient. So maglev trains, instead of rolling, they float. They use these magnetic fields to float. Now, a lot of them use just very powerful permanent magnets, but some of the newest ones actually use superconductors to operate on this levitation principle. And with that, they're able to go really fast. They can go 300 miles per hour, and they can use very little energy because there's no wheels to roll, there's no friction to worry about. It just flies through the air. So maglev trains are something interesting, and you can use it with this sort of levitation principle. What was I going to say next? I don't know. There's all sorts of, one more thing. The adults in the room will know. MRI machines. Anybody had the unfortunateness of having to have an MRI? Maybe not? Good. Lucky. MRI machines, they're like a really special, like a different form of X-rays. They enable you to see what's inside of you. And they need really strong magnetic fields, so like a really, really strong magnet. You can't make that strong of a magnet with just like regular magnets like we have here. So they use superconductors to actually have enough current to flow to be able to create these very, very strong magnetic fields, which then you have the unfortunateness of going into if you're getting an MRI. So superconductivity, since it's one of the few things that we actually encounter in science. If you think about it, barely anything in any sort of scientific principle we have is truly perfect. Right? So we have ball bearings, right, which don't have much friction, but there's still a little bit of friction. We have copper wires, which have very low resistance, but it's not perfect. Superconductivity is one of the few things that's actually truly zero, truly perfect. So you can get cool things. You can get, like I said before, you can get the currents flowing in loops forever. They never stop. You can get ridiculously high magnetic fields. You can get levitation. You can get all sorts of cool effects because it's something that is actually perfect. So it's a very unique phenomenon. We've known about it for about 100 years, but we're still working to make it better. And one of the biggest problems... A railgun? Sure. Let's talk about it afterwards. We'll do some questions after I'm done, and then we can talk. Because actually, it could be useful in a sort of railgun application. Whenever I had this superconductor out, and you noticed how it floated for a while, and then it settled down, and you saw all the steam coming off, any guesses as to what that steam coming off was? Any guesses? Any thoughts? What's actually happening inside of here is there's a liquid. It might look like water if you were to look at it, but it's not water, I assure you. This in here is liquid nitrogen. Now, nitrogen is mostly what we breathe. We breathe 78% nitrogen. But if you take it and you put it into its liquid form, it just becomes just like a liquid, just like water or just like water. It actually looks like water. It's clear. And it's very, very cold. And it cools these materials down so that they become superconducting. And here's why. And here is sort of the problem that we have with superconductivity, and it's what we're trying to fix. Remember how I said how superconductors work because the electrons, instead of fighting their way through one at a time, they pair up and they join together? Well, it turns out that these electrons aren't all that friendly. They're sort of friendly, but not that much. And if it gets too hot, they'll separate away. So if it's really cold, you can imagine like if maybe it's like really cold, or you're out camping. Let's say you're out camping and it's really cold. You might snuggle with somebody else. You might stay close to them to conserve warmth or something. And then once it warms up, you just kind of go away from them because you don't really care. Well, electrons are the same way. So if it gets too warm, the electrons will split up. They'll be back to going through by themselves, and they kind of they kind of shoot themselves in the foot because then they have to have the resistance of going through the wire. So that's the biggest problem. We have to keep it really cold. And if we don't have it cold, then the superconductor won't work. So that's the biggest things that we work on. We try and make, at least here and at any place else that's working on superconductivity research, we try and increase these temperatures basically and make it so that it will be superconducting at still higher temperatures. Basically, we want to make the electrons more friendly.